Okay, so we just saw on the last example that we could approximate sine x using a Taylor polynomial, and the sixth Taylor polynomial we said was x minus 1/6 x cubed plus 1 over 120 x to the fifth. Now we centered this approximator at 0, so we really can only use it for values that are close to 0. So just to remind you, this is what we said. We're looking at sine x and we're trying to compare it to this polynomial. So here's sine, and then our polynomial that seems to be a pretty good indicator, pretty good estimator, just around the origin. So in this example, we're going to use this polynomial to estimate something that you don't know by heart, or that's not on the unit circle. So we're going to use this to approximate the value for sine of 12 degrees. Now we've created all of our Taylor polynomials in radians, so we'll have to go back and do a little adjustment there, but when we do, we should be able to use this as an estimator. So the first thing I've done is converted 12 degrees into radians to get pi over 15. So I am going to use pi over 15. 12 degrees or pi over 15 is pretty close to 0, so it might make sense that this Taylor polynomial would be a good estimator. So I'm taking pi over 15 and I'm plugging it into T6, my sixth Taylor polynomial. Now I just put these values in my calculator, I copied down all of the values that my calculator gave me, and then I rounded to the 6th decimal place because up here it had asked me to round sine 12 to 6 decimal places. So it's hard to say at this point how good this estimate is. So I go to my calculator and I just typed in sine of pi over 15 directly into my calculator, and I copied down all the decimal places that my calculator told me. And what I want you to notice that the estimate, the polynomial estimate, is pretty close to the sine estimate except for the last 2 decimal places. So it appears that if we were rounding to 6 decimal places, that this would have no error at that decimal location. So we'll do one more and then we'll kind of talk about how many decimal places can we go to be confident that we have an estimate that is accurate. So let's just try one more, 20 degrees. Now 20 degrees is a little further away from 0, so we're probably not going to get as great an estimate because we're moving away from that center value that we used to create our Taylor polynomial. But similar to the last example, I went ahead and converted it to radians. So I have pi over 9. It's near a equals 0, but not quite as close as 12 degrees. And I took pi over 9 again and plugged it into my Taylor polynomial. From my calculator, I copied down all of those values, and then I rounded to 6 decimal places because, again, it asked me to do 6 decimal places here. So then I went back to my calculator and I just asked my calculator, hey, what is the sine of pi over 9? Of course, your calculator is estimating this as well, but this is what it told me. And when I look at 6 decimal places, it again appears that this has no error, but you can see the error creeping up right here. 4 decimal places out from the end, whereas up here we only had 2. So it does appear that this is a slightly worse estimate, but maybe not so bad at 6 decimal places. So the question is 2 things. How far can we go out? If we go out 0.3 in both directions, what error do we get in that calculation? Of course, this is in radians. And then later on, what could be our furthest point out, our farthest x value that would satisfy a certain error threshold? So since this Taylor polynomial is alternating positive and negative terms, we can go back and use the alternating series estimation theorem to calculate our maximum error. Now, if you remember what this theorem said back when we were talking about it in the alternating series test, we said, okay, if we have a decreasing function and it's alternating, well, decreasing series, I should say, and the terms are alternating, then they're giving and taking from the true sum in such a way that the remainder term, which is just the difference from the true value and your partial sum, in this case our partial Taylor polynomial, is less than or equal to the absolute value or the distance from 0 of that next term, that n plus 1th term. So what we're looking for is how much error, or what is the remainder in choosing our 6th Taylor polynomial. So we're looking for the actual value of the function and how different that is from our polynomial estimation T6. And looking at the next term in the Taylor series, that next term would be the 7th term, x to the 7 over 7 factorial. I want to talk a little bit about the coefficient here. It's technically a -1, but in absolute value it's a 1. And the reason for that, you might have to flip back to the previous page, but in order for us to get the Taylor coefficient, we need the 7th derivative of x, which is negative cosine x. We're centering our polynomial here at 0. So that numerator of the Taylor coefficient is -1. I've just gone ahead and evaluated that -1 here using the fact that I am looking for absolute value. So what this is saying is that in choosing to use the 6th Taylor polynomial, the maximum error we get is represented by the absolute value of x to the 7 over 7 factorial. So we're being asked here, if we only go a distance of 0.3 from x in either direction, how much error is that? So that means the absolute value or the distance from our center x here is less than or equal to 0.3. So that's the maximum x can take for this particular threshold we're testing. So I plug that in for x, and then I put this into my calculator, 0.3 to the 7th power divided by 7 factorial, which evaluates to 5040, and I get 4.3 times 10 to the -8. What this tells me is that the error occurs in the 8th decimal place. So as long as we stay within 0.3 radians of 0, x equals 0 or a equals 0, we will be confident that our estimate to the 6th decimal place is accurate. Once we get to the 8th decimal place, then we'll start to introduce error, and we no longer may do that. We can do two things to fix that. We can do a larger Taylor polynomial, or we can, of course, shorten our distance from the center. Okay, so now let's talk about how far we can go. So in this last question for this example, it's asking us, all right, let's answer something a little bit differently. What x values could we pick? How far away from 0 could we go if we wanted the error to be less than 0.0001? So in this case, we don't really know our values of x, but we are taking, again, our 6th Taylor polynomial, and we're trying to get the error less than this threshold that was given to us. So we know that our error is bounded by that n plus 1th term in the Taylor series. So that's x to the 7th over 7 factorial. And I'm trying to find for what x values this guy is less than our threshold. So I multiplied both sides here by 7 factorial. So I get the absolute value, or the distance from the center for x to the 7th is less than 0.504. Then in my calculator, I took the 7th root of that. So I see here that if I want to maintain this much accuracy, then I can go to 0.9068. So this is a wider range than 0.3 because we've lessened our accuracy. We're not asking about the 6th decimal place, we're asking about the 4th. So what this is saying is that if we need accuracy to the 4th decimal place, then in radians we could go as far as negative 0.9068 in both directions in radians, or if you convert that to degrees, to about negative 51.9558 degrees and 51.9558 degrees to the right, and we would have accuracy over there to the 4th decimal place.